Tucson, Arizona, the University of Arizona Steward Observatory. The year is 2009. Astronomer Christopher Kochanek is running a survey with an unusual goal. He is not looking for new stars, or new galaxies, or new phenomena in the night sky. He is looking for disappearances. He is watching hundreds of thousands of red supergiant stars in nearby galaxies, year after year, waiting for one of them to vanish. This sounds strange. Stars are not supposed to vanish. Stars are supposed to die in supernova, the most violent explosions in the universe, bright enough to briefly outshine entire galaxies, visible across billions of light years. Massive stars is special. Why? They are supposed to end in a catastrophe, a core collapse, a flash that announces their death to the cosmos. The astronomy textbooks are clear on this. You do not just quietly disappear when you are 25 times the mass of the sun. But Kochanek had been thinking about a theoretical possibility that was quietly troubling to stellar physicists. What if some massive stars did not explode? What if the core of certain massive stars, when it collapsed under its own gravity, formed a black hole so quickly and so completely that the explosion never occurred? What if the star simply fell inward, collapsing straight to a black hole in a fraction of a second, swallowing itself entirely, producing no supernova? What if it simply went dark? This was called a failed supernova. And in the early 2000s, it was a theoretical prediction, derived from simulations of stellar core collapse, with no direct observational confirmation. So Kochanek built a survey to find one. He called it the Large Binocular Telescope Survey for Failed Supernova. He pointed two of the world's most powerful cameras at nearby galaxies and began watching and waiting. In 2009, a red supergiant in the galaxy NGC 6946, about 22 million light-years away, in the constellation Cygnus, brightened. Briefly, a flash of luminosity, a brief and relatively modest outburst, nothing compared to a full supernova. Kochanek's team noted it. They continued watching. Then, over the following years, the star faded, and by 2015, it was essentially gone, not dimmed, not obscured, gone. The star, that had been clearly visible in the images, a red supergiant brighter than 1,000,000 suns, detectable from 22 million light-years away, had vanished from the optical images. Where it had been, there was nothing, or almost nothing. Kochanek stared at the data and thought, this might be it. This might be a star that just fell into a black hole. He was right about the disappearance. Whether he was right about why, that question is still being answered today. Massive stars are supposed to explode. This is not a minor detail of stellar physics. It is one of the most fundamental and most thoroughly tested predictions in all of astrophysics. For over a century, astronomers have watched massive stars reach the end of their lives and detonate in supernovae. Explosions so bright they can be seen from the far side of the observable universe. The physics is understood, the process is modeled, the observations confirm it. And then a star in a galaxy 22 million light-years away quietly disappeared. No explosion, no supernova, no flash, nothing. Just a brightening, a fading, and then silence. For over a decade, the question of what actually happened to N6946BH1 has been one of the most interesting open problems in stellar astrophysics. And in April 2026, a new JWST program was approved specifically to resolve it. The answer is still unknown. But the investigation of this one star has changed what we think we know about how massive stars die. This video is about disappearing stars. Specifically, it is about 3 different stars that have appeared to vanish, in 3 different ways, in 3 different places, studied over 3 different timescales, and what each of their disappearances tells us about the most violent and most poorly understood events in the universe. The first is N6946 BH1, a red supergiant in the fireworks galaxy, 22 million light-years away. It brightened in 2009 and then disappeared from optical view over the following years. JWST found it again in the infrared in 2024, still glowing faintly, still emitting energy, but transformed into something that does not fit any simple explanation. The source of that infrared emission, a failed supernova collapsing to a black hole, a binary stellar merger, a star buried inside a dust cocoon, remains genuinely unresolved. A new JWST observing program, approved in April 2026, is specifically designed to break the deadlock. The second is the luminous blue variable star in the Kinman dwarf galaxy, PHL 293b. Observed consistently from 2001 to 2011, its spectral signatures vanished entirely from observations taken in 2019. No explosion was detected. No supernova was seen. The Centaur, a massive, violently unstable stellar giant in one of the most metal-poor galaxies known, simply stopped producing the spectral features that had marked its presence for a decade. Whether it died quietly, ended an eruption, or was already gone before anyone noticed remains unclear. The third is Assassin-24 FW, a star in our own galaxy that dimmed by 97% between late 2024 and early 2025 before recovering. For 8 months, a star that should have been easily visible became almost invisible, not just dimmed but nearly gone. Ohio State University researchers proposed an explanation in August 2025, a dust cloud transit, but the specific properties of the event remain unusual enough to be scientifically interesting. 3 disappearing stars, 3 different stories, and the question at the center of all 3. When a star vanishes, what is it actually telling us? By the end of this video, you will understand why massive stars are supposed to explode, and what the theoretical alternative, the failed supernova, actually means. You will understand what JWST found when it looked at N6946 BH1 14 years after it vanished. You will understand what the Kinman dwarf galaxy star tells us about the limits of our ability to watch the sky. And you will understand why the resolution of these mysteries, whichever way the data eventually points, will change the way we understand how the universe's most massive objects are born. So, what actually happens when a massive star vanishes without exploding? How does a star the size of 25 suns simply disappear from optical view without producing the supernova that stellar physics says it should? What did JWST find when it looked at the position of N6946 BH1 in 2024, 14 years after the star vanished? And why did its findings deepen rather than resolve the mystery? What is a failed supernova? And if N6946 BH1 is one, what does its existence mean for our understanding of how black holes form? What happened to the massive star in the Kinman dwarf galaxy? And why did the community not notice it was gone for 8 years? And what does the 97% dimming of Assassin-24 FW tell us about how many apparent disappearances turn out to be something less dramatic, and how you tell the difference? This is not a video about aliens or cosmic horror. Stars vanish for entirely physical reasons: dust obscuration, stellar mergers, the quiet collapse of a core that does not detonate. None of these require any departure from known physics. None of them are dangerous to Earth. None of them are evidence of anything beyond the extraordinarily varied and extraordinarily violent processes by which the universe's most massive objects meet their ends. But this is also not a video that treats stellar disappearances as merely routine. The specific case of N6946BH1 is genuinely unresolved after 14 years of study, including 14 years of data from some of the world's most powerful telescopes. It may represent the first confirmed failed supernova in history, a theoretical prediction of stellar physics that has been looking for an observational confirmation for decades. Or it may be a stellar merger, a dust cocoon, or something else entirely. The honest answer, in May 2026, is that we do not yet know. And the investigation of that honest uncertainty is more interesting than any settled story would be. Stay with me. Before we go deeper into the physics, if these are the kinds of stories that pull you in, real astrophysics at the edges of what we understand, told honestly and without false resolution, hit subscribe. Galaxy Pulse goes beyond the headlines every single time. We will not pretend a mystery is solved when it isn't, but we will tell you everything we do know, why the uncertainty matters, and what the investigation is teaching us regardless of which way it resolves. Now, back to the fireworks galaxy and THE star that disappeared without saying goodbye. To understand why N6946BH1 disappearance is significant, why it is not just unusual but potentially transformative for our understanding of how massive stars die, we need to understand what is supposed to happen when a massive star reaches the end of its life. The physics of stellar death is one of the great achievements of 20th century astrophysics. It is also, as N6946BH1 is demonstrating, somewhat incomplete. Stars are fusion engines. For most of their lives, they exist in a state of dynamic equilibrium. The gravitational pressure trying to collapse the star inward is balanced by the outward pressure of radiation and hot gas produced by nuclear fusion in the core. The Sun has been in his equilibrium for approximately 4-6 billion years, and will remain in it for another 5 billion or so. It burns hydrogen in its core, producing helium, and the energy of that reaction props the star up against its own gravity. Massive stars, stars more than 8 times the mass of the Sun, play a different and more dramatic game. They burn hotter, faster, and more recklessly. A star, 25 times the mass of the Sun, burns through its hydrogen fuel in just a few million years, compared to the 10 billion years the Sun enjoys. But hydrogen is only the first fuel. When the hydrogen in the core runs out, the star does not simply stop. Gravity compresses the core further. The temperature rises. And when the temperature is high enough, helium begins to fuse, producing carbon and oxygen. Then the carbon burns, then the oxygen, then neon, then silicon. Each successive fuel burns faster than the last, at higher temperatures, producing less energy per reaction. The end of this sequence arrives fast. Silicon, burning in the core of a massive star, produces iron. And iron is the end of the line. Iron fusion is endothermic. It absorbs energy rather than releasing it. When the core of a massive star becomes iron, fusion stops. There is no next fuel. Nothing to provide the outward pressure that has balanced gravity for millions of years. The core collapses. In less than a second, faster than you could blink, faster than any earthquake, faster than almost any physical process you could name, the iron core collapses from roughly the size of Earth to roughly the size of a city. The protons and electrons in the iron nuclei are forced together to form neutrons. The core becomes a neutron star, an object of extraordinary density, and the collapse stops abruptly as the neutron star's nuclear forces resist further compression. The material falling inward bounces off the suddenly rigid neutron star. A shockwave propagates outward through the star's outer layers. The shockwave blows the star apart. This is a core collapse supernova. The energy released is almost incomprehensible, approximately 10 to the power of 44 joules. More energy than the Sun will radiate across its entire 10 billion year life. For weeks, the exploding star can outshine the entire galaxy containing it. The JWST material races outward at thousands of kilometers per second, eventually forming a supernova remnant that expands across light years. For most massive stars, this is the ending, but not all of them. In some theoretical models, the collapsing core produces a black hole rather than a neutron star. The collapse is more complete, the bounce weaker, the shockwave insufficient to blow the star apart. The outer layers fall back inward. The entire star disappears into the newly formed black hole, not in a blaze of energy, but in a drawn-out implosion. Perhaps with a brief dim flash as material briefly accretes onto the black hole's surface, and then nothing, a failed supernova. The prediction is real. The physics is sound. And for decades, it had no confirmed observational example. Under normal conditions, meaning the standard core collapse supernova scenario, here is what happens at the end of a massive star's life. The star brighten is dramatically. The supernova reaches peak luminosity within weeks, often becoming bright enough to be seen with the naked eye from the other side of the Milky Way, and visible in telescopes from tens of millions of light years away. The light curve, the brightness as a function of time, follows a characteristic shape that depends on the star's mass and composition. The peak brightness, the rate of decline, and the eventual fade all follow predictable patterns that astronomers use to identify and study supernova across cosmic distances. What happened to N6946 was almost the opposite. In 2009, the star brightened, but modestly, perhaps 4 times its typical luminosity over a period of months, then declining. No supernova. No peak brightness outshining the galaxy, just a brightening, then a slow decline. By 2015, the star was gone from optical images. Not just dimmed, not just at the edge of detection, gone. Where images from 2007 showed a clear point source, a red supergiant several hundred times brighter than the Sun, detectable across 22 million light years. Images from 2015 showed nothing at all at the same position. No explosion, no flash, no expanding shell of ejecta, just absence. To appreciate how strange this is, consider what it would look like if the Sun simply vanished one day. No nova, no planetary nebula, no slow fade over billions of years. Just, there one day, gone the next. On cosmic timescales, that is roughly what N6946 did. It was there, it brightened, slightly. And then, over 6 years, it disappeared. Kachenek's survey had been looking for exactly this kind of disappearance for years, and now they had a candidate. The story of N6946 begins properly in 2007, with a baseline observation. The Large Binocular Telescope Survey for Failed Supernova was designed with a specific methodology. Every year, the team took images of a set of nearby galaxies and compared the new images to the previous years. Any star that brightened significantly was flagged as a potential supernova. Any star that disappeared was flagged as a potential failed supernova candidate. NGC 6946, a large, face-on spiral galaxy in the constellation Cygnus, was one of the survey targets. Nicknamed the Fireworks Galaxy for its extraordinarily high rate of observed supernova, NGC 6946 has hosted 10 confirmed supernova in the past century, more than any other galaxy in the known nearby universe. It was an obvious target for a survey looking for stellar deaths. In the 2007 baseline images, A red supergiant was clearly visible at a specific position in NGC. Red supergiant, approximately 25 solar masses, with a luminosity of approximately 430,000 times the Sun. A large star, not unusual in NGC 6946, not obviously different from thousands of other red supergiants in the galaxy. In 2009, the star brightened. The team flagged it. The brightening was roughly consistent with an LBV eruption, a luminous blue variable outburst, or with a common envelope event in a binary system. It was not obviously the beginning of a supernova. They continued monitoring. Year after year, the brightness declined. The star did not brighten again, it faded. By 2012, it was significantly fainter. By 2015, deep imaging with the Hubble Space Telescope showed essentially nothing at the position where the star had been. The optical source had vanished. Kachenik and his team published their analysis in 2017. The conclusion was carefully worded, but unambiguous in its implication. N6946BH1 is a disappearing supergiant star and failed supernova candidate, formerly seen in the galaxy NGC 6946. The star had no T-produced a supernova. It had not produced any bright optical transient consistent with a supernova. It had simply faded and vanished. The team proposed that the most likely explanation was a failed supernova. The star's core had collapsed to a black hole without producing the shockwave that drives a conventional supernova. The brief 2009 brightening might have been the last gasp of energy released as the outer envelope of the star fell into the nascent black hole before darkness claimed the position entirely. But there was a complication. The star had not entirely disappeared. Even in the 2015 Hubble images, there was a faint infrared source at the position, not in optical wavelengths, no visible light. But in the near-infrared, something was still glowing, faintly, much fainter than the original star, but present. This infrared remnant was the first complication in what had seemed like a clean story. A star that fell completely into a black hole should leave nothing behind to glow. The infrared emission suggested that something was still there, something hot enough to emit, but obscured in optical wavelengths by dust. The interpretation remained. Probable failed supernova, with the infrared emission coming from dust heated by the black hole's accretion, or by the remnant of the star's envelope. Possible, but uncertain. Then, in 2023, JWST looked at N6946BH1. N6946BH1 is the first plausible candidate for a failed supernova, a peculiar event in which a massive star disappears without the expected bright supernova, accompanied by collapse into a black hole. Following a luminous outburst in 2009, the source experienced a significant decline in optical brightness, while maintaining a persistent infrared presence. JWST showed for the first time that all previous observations of BH1, pre- and post-disappearance, are actually a blend of at least three sources. What Hubble had seen as a single-point source was, at JWST superior resolution, resolved into multiple objects. The disappeared star itself was now distinguishable from its neighbors, and what JWST found at the specific position of N6946BH1 was not nothing. Recent JWST imaging revealed a luminous infrared source at the location of failed supernova candidate N6946BH1. While significantly fainter than the progenitor, 13 to 25% of the bolometric luminosity. The spectral energy distribution is consistent T with both a failed supernova and a stellar merger, or outburst event. The star is not gone. It is still there, in the infrared. But it is completely different, much fainter in the optical, much brighter in the mid-infrared than the original progenitor models predicted. And here is where the mystery deepened rather than resolved. At present, the interpretation of N6946BH1 remains uncertain. The observations match expectations for a stellar merger, but theoretical ambiguity in the failed supernova hypothesis makes it hard to dismiss. Failed supernovae collapsing to a black hole, with the black hole accreting in falling material and producing infrared emission. Or a stellar merger, two stars in a binary system spiraling together and merging, producing a bright transient followed by a dust-enshrouded merged remnant. Both scenarios can account for what JWST observed. Curiously, observations taken 1 month later in matching filters revealed a 50% flux reduction in the shortest MIRI filter at 5-6 microns. The infrared source was changing on a timescale of weeks, which adds yet another constraint that any explanation needs to accommodate. The mystery is real, it is unresolved. And a new JWST observing program, Program 7648, approved by the Space Telescope Science Institute in April 2026, led by BSER, is specifically designed to take a full mid-infrared spectrum of the remaining source, which should finally reveal whether the spectral features are consistent with PAH emission from a stellar merger, or with the infrared accretion signature of a failed supernova. As of May 2026, the answer is still unknown. Let us make the key physics concrete, because two concepts in this story are essential to understanding why the mystery matters. Think of it this way. Imagine a massive skyscraper, 25 times taller than a normal building, held up by internal pressure. The structural supports are burning fuel continuously, and the heat and pressure of that burning is what keeps the building standing. If the fuel runs out suddenly, the building collapses inward. For a normal building, the collapse would produce an enormous explosion as the floors pancake onto each other and the energy is released. That is the supernova model. The building collapses. The energy of the collapse blows the walls outward, and the explosion announces the building's end to everyone within sight. Now, imagine a different building. One whose internal structure is such that when the fuel runs out, the collapse is so complete and so fast that the explosion never escapes. The walls fall inward faster than the shockwave can propagate. The building swallows itself. Nothing escapes. The building disappears, leaving only a small, dark, extraordinarily dense remnant where it used to be. That is the failed supernova model. There are three things you need to understand clearly. The first is why some massive stars might fail to explode. The outcome of a core collapse, supernova, or failed supernova, depends on the details of the collapse. The mass of the collapsing core, the rotation rate of the star, the mass of the outer envelope, and the specific properties of the bounce shock, that faux RMS, when the collapsing core hits the newly formed neutron star. In simulations, stars above a certain threshold mass, roughly 25 to 40 solar masses, though the exact threshold is uncertain, and mass is not the only factor, are more likely to produce fail-ed supernova. Their cores are simply too massive for the bounce shock to overcome the infalling material. The star collapses entirely. N6946BH1 progenitor was approximately 25 solar masses, right in the range where failed supernova are theoretically expected to occur. The second thing to understand is what a stellar merger looks like. When two massive stars in a binary system lose orbital energy through the emission of gravitational waves, through interaction of their stellar winds, or through mass transfer between the stars, they can spiral inward and eventually merge. The merger releases an enormous amount of energy, producing a luminous transient, an intermediate luminosity optical transient, sometimes called a luminous red nova, followed by a dramatically transformed merged star embedded in an expanding shell of dust and gas. The dust obscures the optical emission but re-radiates as infrared. The merged star is much larger, redder, and surrounded by material that continues to emit in the infrared for years to decades after the merger. The 2009 brightened ING of N6946BH1 is consistent with either a stellar merger or the last brighten ING of a star about to undergo a failed supernova. The subsequent infrared emission is consistent with either a dust-obscured merged remnant or a black hole accreting in falling material. JWST cannot currently distinguish between these two scenarios from photometry alone. The third thing to understand is why the distinction matters enormously. If N6946BH1 is a failed supernova, it is the first confirmed observational example of a massive star collapsing directly to a black hole without a supernova. This would directly confirm a theoretical prediction that has been in the literature for decades. It would help explain a known puzzle in stellar physics. Observations of supernova progenitors suggest that the most massive red supergiants, those above roughly 17 solar masses, do not appear to produce supernova at the expected rate. This is the RSG problem, the red supergiant problem, and failed supernova in the highest mass range would explain the discrepancy. If N6946BH1 is a stellar merger, it is the most massive and most well-documented stellar merger ever observed, with JWST quality observations that will constrain merger physics in entirely new ways. Either answer is scientifically transformative. Neither answer is boring. Here is where the stakes rise in a way that connects a single disappearing star to some of the biggest questions in astrophysics. The rate at which massive stars produce supernova versus the rate at which they collapse quietly to black holes has enormous implications for the chemical evolution of the universe. Supernova are not just spectacular events. They are the primary mechanism by which the universe distributes the heavy elements produced by stellar fusion. Carbon, oxygen, nitrogen, silicon, iron, all of the elements heavier than hydrogen and helium that make up planets and bodies and everything we interact with, were forged in the cores of massive stars and dispersed into the interstellar medium when those stars exploded. Without supernova, the universe's heavy elements would remain locked inside black K holes. If a significant fraction of massive stars fail to explode, if they collapse directly to black holes, taking their nucleosynthetic products with them, then the universe is producing heavy elements less efficiently than models predict. The chemical history of galaxies would need to be revised. The predictions for what kinds of planets form, in what abundances, around what kinds of stars, would change. Estimates from failed supernova models suggest that somewhere between 10 and 30% of massive stellar deaths may be quiet. Failed supernova producing black holes without bright explosions. This is a significant fraction. It would explain some no-end discrepancies between observed supernova rates and what population synthesis models predict. It would change how we model galaxy chemical evolution. N6946BH1, if confirmed as a failed supernova, would be the first direct observational anchor for this rate. N6946BH1 is the most studied disappearing star, the most documented, the one for which JWST has now returned data. The one for which a new observing program was approved in April 2026, specifically to resolve the remaining ambiguity. But it is not the only star that has vanished. In the Kinman dwarf galaxy, a small, metal-poor galaxy more than 75 million light-years away. A different kind of stellar disappearance occurred. Not a red supergiant in a star-rich spiral galaxy, carefully watched by a dedicated survey, but a single-mass, sieve luminous blue variable star, observed intermittently over a decade, whose spectral signatures simply ceased to appear in data collected in 2019. And the specific way this star vanished, not by fading slowly, but by dropping out of spectroscopic observations entirely, raises a different set of questions about what the universe's most massive stars do at the ends of their lives. The Kinman dwarf galaxy, officially designated PHL 293b, is not the kind of place where you would ordinarily go looking for stellar mysteries. It is a compact, irregular dwarf galaxy, approximately 75 million light-years from Earth. It is small, faint, and metal-poor, meaning it contains very little in the way of the heavy elements that accumulate in galaxies over time, as successive generations of stars live and die, and enrich the interstellar medium with their nucleosynthetic products. Metal-poor environments are, in some sense, primitive. They resemble the early universe, before billions of years of stellar evolution had distributed the heavier elements that now dominate the chemistry of galaxies like the Milky Way. In metal-poor environments, massive stars behave differently than in metal-rich ones. Their stellar winds are weaker, heavy elements are what drive stellar winds, and without them, massive stars in metal-poor galaxies retain more of their mass throughout their lives. They can grow larger, more luminous, and more unstable before their deaths. The most extreme class of massive star, the luminous blue variable, or LBV, is particularly prone to violent eruptions and instabilities in metal-poor environments. From 2001 to 2011, a luminous blue variable star was observed in the Kinman dwarf galaxy. It was not observed directly, at 75 million light-years. Individual stars in the Kinman dwarf are far too faint for direct imaging with current telescopes. What was observed were the spectral signatures of the star, the specific wavelengths of light that the star's atmosphere absorbed and emitted, visible in the combined spectrum of the galaxy's small stellar population. The star was in an eruptive state, its spectrum showing the broad Balmer hydrogen emission lines with P Cygni profiles that are the characteristic signature of a massive star in outburst, with a dense, high-velocity wind. From the years 2001 to 2011, astronomers were picking up consistent evidence that a large and rather unstable luminous blue variable star resided in the dwarf galaxy. Blue variables are unstable stars, displaying dramatic shifts in their brightness and spectra, or thermal radiation emitted by the star. The star was there, consistently, year after year. Its spectral signatures were detectable in every observation. Then, in 2019, a team led by Andrew Allen at Trinity College Dublin took new spectra of the Kinman dwarf galaxy using the Espresso and X-Shooter instruments on ESO's Very Large Telescope in Chile. The sudden disappearance of the stellar signatures was found from the 2019 spectra. In particular, the broad hydrogen lines with P Cygni profiles that had been associated with the massive luminous blue variable star. The star's spectral signatures were gone, not weakened, not shifted, gone. The broad emission features that had been present in every observation from 2001 to 2011 were absent from the 2019 spectrum, where the star's atmosphere had been imprinting its chemistry on the galaxy's light for a decade. There was now silence. The gap between the last positive observation in 2011 and the first non-detection in 2019, 8 years, meant that the disappearance could have occurred at any point in that interval. Nobody had been watching continuously enough to catch the moment. The alternative explanation for the disappearance of the LBV in PHL 293b is an undetected supernova explosion. Burke et al. 2020 favor this hypothesis, suggesting that a supernova-Ian event occurred between 1995 and 1998, during which no photometry is available. In this case, the broad components seen in the bomber lines between 2001 and 2011 would come from interaction between the supernova ejecta and a dense circumstellar medium. The two leading hypotheses are thus: the star has collapsed to a black hole without a bright supernova, or the star exploded in an undetected supernova before 2001, and what was being observed from 2001 to 2011 was not the star itself, but the expanding supernova ejecta, interacting with surrounding material. In this second scenario, the star was already gone before the observations began. The spectral signatures were the echoes of an explosion that nobody saw. Scientists think this could indicate that the star became less bright and partially obscured by dust. An alternative explanation is that the star collapsed into a black hole without producing a supernova. What's next? Astronomers will have to investigate this mysterious case further in order to figure out what exactly happened to this once giant star. ESO's extremely large telescope will be capable of observing stars in distant galaxies such as the Kinman dwarf, helping to solve cosmic mysteries such as this one. The ELT, expected to begin science operations in the late 2020s, will have the angular resolution and light gathering power to potentially detect the individual star in the Kinman dwarf directly, or to confirm its absence for the first time. Until that data arrives, the mystery of the Kinman dwarf's vanished LBV remains genuinely open. Not every stellar disappearance is a mystery. In the autumn of 2024, the All-Sky Automated Survey for Supernova, Assassin, a network of robotic telescopes specifically designed to monitor the sky continuously for transient events, detected something unusual in our own galaxy. A star, designated Assassin-24 FW, began to fade. Not gradually, rapidly. Located about 3,000 light-years from Earth, this star pulled off an incredible disappearing trick between late 2024 and early 2025. For 8 months, it dimmed by an astounding 97% before returning to its normal brightness. To put this in perspective, imagine a bright streetlight suddenly becoming as dim as a birthday candle. A 97% dimming is extraordinary. Most variable stars fluctuate by modest amounts, fractions of a magnitude, rarely more than a factor of a few in brightness. A dimming by a factor of 33, which is what a 97% reduction represents, is far outside the normal range of stellar variability. For 8 months, Assassin-24 FW was almost invisible. Then, gradually, it recovered. By early 2025, it was back to its normal brightness. The astronomical community took notice. Was this another disappearing star in the mold of N6946BH1? Was this a failed supernova unfolding in our own backyard? Or was it something else? What made this event particularly puzzling was that the color of the star's light remained unchanged during its dimming. This crucial clue told scientists that the star itself wasn't changing or dying, something else was blocking our view. This is the key diagnostic. When a star dims because of an internal change, the core exhausting fuel, the atmosphere changing temperature, the star entering a new phase of its evolution, the color of the star's light changes along with its brightness. Cooler stars are redder. Hotter stars are bluer. If you dim because you are cooling, you redden as you dim. If you dim because something external is blocking your light, and that external something absorbs all wavelengths equally, as dust does, your color stays the same, while your brightness drops. Assassin -24 FW, dimmed without changing color. Something was blocking its light, not the star dying, not the star changing, an external obstruction. An international team, led by scientists at The Ohio State University, suggests that because the color of the star's light remained unchanged during its dimming, the event wasn't caused by the star evolving in some way, but by a large cloud of dust and gas around the star that occluded Earth's view of it. The explanation, published in August 2025 in the Open Journal of Astrophysics, proposes that a cloud of dust and gas in the star's immediate environment, possibly ejected by the star itself at an earlier time, or possibly a disk of material in an associate binary system, passed between the star and Earth, blocking the majority of the star's light for the duration of the transit. The event is similar, in its basic mechanism, to the famous dimming of Betelgeuse, the Great Dimming of 2019 to 2020, when Betelgeuse dimmed by roughly 38% due to a combination of a surface convection cell and dust ejection. Assassin -24 FW's dimming was much more extreme, 97% rather than 38%, but the same basic mechanism appears to apply. Assassin -24 FW did not die. It was occluded. The story of Assassin -24 FW is interesting not as a mystery in the same category as N6946 BH1. Its explanation, while not yet definitively proven, is entirely plausible and consistent with known stellar behavior. It is interesting as a methodological lesson. The color constancy, the fact that the star did not redden as it dimmed, was the diagnostic that ruled out a stellar death scenario quickly and pointed investigators toward the external obstruction explanation. This is how stellar disappearances are investigated, not by jumping to the most dramatic explanation, but by carefully cataloging the observable properties, light curve, color evolution, spectral changes, and using those properties to distinguish between a finite set of known scenarios. For N6946 BH1, that methodology has not yet produced a definitive answer. The infrared source remaining at the star's position is consistent with both the failed supernova and the stellar merger scenario. Future observations, specifically the JWST spectroscopy from programs 76 and 48, may provide the diagnostic that finally resolves the ambiguity. For Assassin -24 FW, the methodology worked. The color constancy pointed to dust. The explanation arrived in months rather than decades. The star is still there. The comparison between Assassin -24 FW and N6946 BH1 illustrates something important. Not every dimming star is a cosmic mystery, but some of them are. And knowing the difference requires the kind of careful, patient, multi-wavelength investigation that the JWST era is making possible for even the most distant and most challenging objects. N6946 BH1 is not an isolated anomaly. It is the most dramatic example of a broader phenomenon that stellar astrophysicists have been struggling with for years. The apparent deficit of very massive red supergiant stars among confirmed supernova progenitors. The logic goes like this: supernovae are common. Our galaxy produces roughly 2 or 3 per century. We miss most of them because dust in the Milky Way obscures the view. In nearby galaxies, where we can observe the sites of supernova before and after the explosion, astronomers have been building a catalog of supernova progenitors, the specific stars that were visible at the supernova site before the explosion. This catalog is assembled from archival Hubble images, taken years or decades before the supernova, that happened to show W, the progenitor star. The catalog tells a story that does not quite match theoretical predictions. Stellar models predict that massive stars above roughly 17 to 25 solar masses, depending on various model assumptions, should end their lives as red supergiants and then explode in core collapse, supernova. We should be finding very luminous red supergia NTS in the progenitor catalog, but we are not. The most luminous red supergiants, the most massive ones, are systematically underrepresented among observed supernova progenitors. This is the RSG problem, the red supergiant problem. Several explanations have been proposed. One is that very massive red supergiants, in the final stages before explosion, may be surrounded by so much self-ejected dust that they become invisible in optical images. Invisible to the archival Hubble surveys used to identify progenitors. The star is there, it is simply hidden. Another explanation is the failed supernova hypothesis. If stars above roughly 20 to 25 solar masses preferentially collapse directly to black holes without producing bright supernova, they would be absent from supernova progenitor catalogs, not because THI are invisible, but because they never explode. They simply disappear. N6946 BH1, with its progenitor mass of approximately 25 solar masses, sits right at the mass threshold where the failed supernova hypothesis predicts the highest probability of quiet collapse. Its behavior, a modest brightening, followed by slow fading to optical invisibility, is exactly what a failed supernova should look like. And the infrared remnant found by JWST, the glowing source at 13 to 25% of the progenitor's luminosity, is consistent with either a black hole heating in falling material or a merger remnant surrounded by dust. The failed supernova hypothesis, ACOM, moderates the infrared data, but so does the merger hypothesis. There is a related phenomenon worth understanding in this context: the luminosity gap in supernova progenitors. When astronomers look at the confirmed progenitor catalog, they find a puzzling absence of progenitors above approximately 17 solar masses in optical wavelengths. Progenitors up to about 17 solar masses are found. Above that threshold, the catalog is surprisingly sparse. Some researchers interpret this as evidence that stars above 17 solar masses are typically very dusty in the final phase before explosion, hidden by circumstellar dust. Others interpret it as evidence that stars above this mass threshold P referentially undergo failed supernova. The JWST era is beginning to provide new data on this. JWST, infrared sensitivity, and angular resolution allow it to detect and characterize very dusty, very massive stellar progenitors that were invisible to Hubble's optical cameras. And it allows it to look at post-disappearance sites, like N6946 BH1, with the sensitivity to detect faint infrared remnants that no previous instrument could characterize. The 2024 Bieser et al. JWST study of N6946 BH1 is the first result of this kind. It will not be the last. Kachenek's failed supernova survey has now been running for nearly 2 decades, and several other candidate disappearing stars have been identified in the dataset. As JWST is applied to each of them, a statistical picture will begin to emerge. How often do massive stars vanish without exploding? The answer, which N6946 BH1 may or may not help settle, has implications for stellar evolution, black hole formation rates, the chemical enrichment history of galaxies, and the expected rate of gravitational wave events from binary black hole mergers. The question is large. The star that might answer it has already disappeared. There are 3 interpretations of what N6946 BH1 disappearance and subsequent JWST detection actually mean. They represent the current state of scientific debate, not fringe versus mainstream, but three genuinely viable scenarios, each consistent with available data, each with different implications for stellar physics. The first interpretation is the failed supernova, the collapse of the stellar core to a black hole without a bright supernova. In this view, N6946 progenitor, red supergiant, at approximately 25 solar masses, experienced a core collapse in which the bounce shock was insufficient to drive a conventional supernova explosion. The core collapsed to a black hole. The outer envelope E of the star fell inward. The brief 2009 brightened. Ing was the accretion of the outer envelope onto the forming black hole, releasing a small amount of energy before the material was swallowed. The subsequent infrared emission comes from material that was N0 swallowed, the outermost envelope, ejected during the 2009 brightened Ing, now forming a dust shell around the black hole, illuminated by continued accretion. The theoretical ambiguity in the failed supernova hypothesis makes it hard to dismiss. The supporting evidence is the progenitor mass, right in the theoretical range for failed supernova, the absence of a bright supernova, the modest 2009 brightened Ing, and the subsequent disappearance from optical view. The weakness is that the JWST infrared luminosity of 13 to 25% of the progenitor is higher than many failed supernova models predict for the infrared emission from a black hole, accreting a small amount of fallback material. The second interpretation is a stellar merger, two stars in a binary system spiraling together. In this view, N6946 was a binary system, a red supergiant with a companion star. As the companion spiraled inward through the extended atmosphere of the red supergiant, it triggered the 2009 brightened Ing as it plunged into the envelope. The two stars emerged. The merged remnant, initially very hot and luminous, quickly became enshrouded in dust from the ejected envelope material. The optical emission was absorbed by the dust. The dust re-emits in the infrared. The infrared source, at 13 to 25% of the progenitor luminosity, is the merged remnant, cooling inside its dust cocoon. The supporting evidence is the JWST mid-infrared spectral energy distribution, which shows features consistent with PAH emission, polycyclic aromatic hydrocarbons that typically form when dust is illuminated by ultraviolet radiation. A stellar merger while D produce a hot merged remnant capable of illuminating surrounding dust and producing PAH emission. A black hole accreting at low rates would produce different spectral features. The weakness is that the variability of the infrared source, a 50% flux reduction in one MIRI filter between observations taken 1 month apart, is difficult to explain in the merger scenario. Merged remnants should fade smoothly, not vary dramatically on month timescales. The third interpretation is a heavily dust-obscured surviving star. The LBV, or red supergiant, is still present, but hidden behind a dust cocoon formed during the 2009 outburst. In this view, the 2009 brightened Ing was an LBV-type eruption in which the star ejected a large amount of material. This material formed a dust shell around the star. The star is still there, burning steadily, but the dust shell absorbs essentially all of its optical emission and re-radiates it at infrared wavelengths. The star has not died, it is simply hidden. The supporting evidence is the relatively high luminosity of the infrared source. 13 to 25% of the progenitor is more than many post-death scenarios predict, and the fact that surviving LBVs in dust cocoons have been observed in other galaxies The weakness is that a surviving star in a dust cocoon would be expected to emit consistently in the infrared without dramatic week-to-month variability. The observed 50% flux reduction in 1 month is hard to explain by the simple dust cocoon model. Here is what is worth saying about all 3 scenarios. Each of them, if confirmed, would be an important result for stellar astrophysics. A confirmed failed supernova would be a landmark, a stellar merger of this mass, and at this proximity, would be an extraordinary observational dataset for merger physics. Surviving LBV in a dust cocoon would constrain the specific physics of LBV outbursts in ways that current models need. The universe does not care which of these scenarios is easier for astronomers to explain. It simply did what it did to N1646BH1 in 2009. And now, 14 years later, the most powerful infrared telescope ever built is still trying to understand what that was. The mid-infrared spectrum from JWST program 7/48 will reveal whether or not there are PAH features present in the spectral energy distribution, and break the degeneracy between the merger and failed supernova scenarios. The answer is coming, it is not here yet. And the investigation of this question, the careful, patient, instrument-limited work of distinguishing between 3 scenarios, each capable of accounting for most of the available data, is exactly what science looks like when it is doing its most important work at the frontier of the unknown. After everything we have seen, N1646BH1 disappearance, the JWST infrared detection, the Kinman dwarf vanished LBV, the Assassin-24 FW dust transit, the RSG problem, the 3 competing interpretations, the question is no longer whether stellar disappearances are scientifically important. They are. The question is what the universe is actually doing when a star simply stops being there. And here is where the story takes a turn that most coverage has never gotten. 2. Remember what we asked at the start of this video, what actually happens when a massive star vanishes without exploding? What did JWST find at N1646BH1, 14 years after it disappeared? And what does the answer, whichever way it eventually resolves, mean for our understanding of how the universe's most massive stars die? After tracing this story from Kachenek's 2009 detection of the brightened, through the years of fading to optical invisibility, through the 2017 failed supernova proposal, through the 2023-2024 JWST observations revealing a persistent and variable infrared source, through the Kinman dwarf's vanished luminous blue variable, through Assassin-24 FW's dust occultation explanation, through the red supergiant problem, through the 3 competing interpretations of what N1646BH1 actually is. Here is what we now can. And, just as importantly, here is what we still do not. We know N1646BH1 progenitor, a 25 solar mass red supergiant, brightened modestly in 2009, and then faded from optical view by 2015. Confirmed. We know JWST detected a persistent infrared source at the position in 2023, at 13 to 25% of the progenitor's luminosity, with spectral features consistent with PAH emission. Confirmed. We know the source varies on month timescales, a 50% flux drop in one filter between observations a month apart. Confirmed. We do not know whether N1646BH1 is a failed supernova, a stellar merger, or a dust-obscured surviving star. Genuinely unresolved. We know JWST program 7/48, approved April 2026, is specifically designed to obtain the mid-infrared spectrum needed to break this degeneracy. That is where the science currently sits. Here is the strange thing about how disappearing stars have been covered in popular media. The coverage of N1646BH1 peaked around 2017, when the original A Disappearing Star paper was published, framed in headlines as "Star Vanishes." Scientists believe it became a black hole without exploding. This framing was not wrong, but it was premature. It presented the failed supernova hypothesis as a conclusion rather than the leading candidate among several possibilities. The 2024 JWST results, which complicated this picture considerably, received far less coverage than the original 2017 story. Most people who heard "star vanished, became a black hole" in 2017 never heard the 2024 update. Actually, there's still something here, and we don't know what it is. Here are the specific things that popular coverage has consistently missed. The first is the persistent infrared source itself. The popular narrative of N1646BH1 is "star disappears, becomes invisible black hole." The reality, as of 2024, is a star disappears from optical view, but something, possibly a black hole accreting material, possibly a merged stellar remnant, possibly a surviving star in a dust cocoon, remains detectable in the infrared, and we don't yet know which. This is a meaningfully different and more interesting story, and it is almost entirely absent from popular coverage. The second is the stellar merger possibility. Most popular treatments of N1646BH1 present the failed supernova interpretation as settled or near settled. The 2024 JWST paper explicitly states that the data matches expectations for a stellar merger, and that theoretical ambiguity makes the failed supernova hypothesis hard to dismiss, not the other way around. The merger hypothesis is, if anything, slightly favored by the specific spectral features observed. This nuance is essentially absent from popular coverage, which continues to describe N1646BH1 as the star that became a black hole, as though this were established fact. The third is the Kinman dwarf parallel. The vanished luminous blue variable in PHL2E93b receives some coverage as an independent story, but it is almost never connected to N1646BH1 as part of a broader pattern of unexplained massive star disappearances. The two cases, a red supergiant in a star-forming spiral galaxy and a luminous blue variable in a metal-poor dwarf galaxy, represent different evolutionary pathways and different observational challenges. But together, they illustrate how much remains unknown about how massive stars end their lives, especially in galaxies and at distances where individual stars cannot be directly resolved. The fourth is Assassin-24FW's relevance as a contrast case. The August 2025 explanation of Assassin-24FW's 97% dimming as a dust transit received decent coverage in its own right, but it has never been connected to the broader disappearing star narrative as a methodological lesson. The color constancy diagnostic that resolved Assassin-24FW quickly is exactly the kind of analysis that, when applied to N1646BH1 infrared source, has not yet produced a clean answer, which is itself informative about how much harder the N1646BH1 case is. The fifth, and perhaps most significant, is the existence of JWST program 7648 itself, a new, specifically designed observing program, approved in April 2026, with the explicit goal of breaking the degeneracy between the merger and failed supernova scenarios for N1646BH1. Represents the scientific community's active, ongoing effort to resolve this mystery. This program has received essentially no popular coverage. Most people who know about N1646BH1 at all believe the story ended in 2017, with the scientists found a star that became a black hole. The story did not end. It is, if anything, more reopened now than it was in 2017, and a specific, dated observational program exists to address it. The most significant recent development in the N6946BH1 story is JWST program 7648, approved on April 16, 2026, with Emma Bieser as principal investigator. The program's stated goal, as recorded in the proposal abstract, is direct. The mid-infrared spectroscopy will reveal whether or not there are PAH features present in the spectral energy distribution, and break the degeneracy between the merger and failed supernova scenarios. This is significant for several reasons. First, it represents a direct follow-up to the 2024 Bieser et al. Results. Using JWST medium resolution spectrometer, the MISES mode of the MIRI instrument, to obtain a full spectrum, rather than the broadband photometry used in the initial observations. Photometry tells you how bright an object is in a few wavelength bands. Spectroscopy tells you the detailed shape of the emission across a continuous range of wavelengths, which is far more diagnostic for distinguishing between physical processes. Second, the specific diagnostic, PAH features, is well motivated. Polycyclic, aromatic hydrocarbons produce characteristic emission features when illuminated by ultraviolet radiation from a nearby hot source. A stellar merger remnant, which would be hot in its early post-merger phase, would illuminate surrounding dust and produce clear PAH features. A black hole accreting at a low rate, without a hot central illuminating source, would be less likely to produce the same PAH signature. The infrared emission would instead be dominated by a different process, likely thermal emission from an accretion-heated dust shell with a different spectral shape. If the MISES spectrum shows clear PAH features, this would favor the stellar merger interpretation. If it shows a featureless or differently shaped continuum more consistent with reprocessed accretion luminosity, this would favor the failed supernova interpretation. Third, the timing of the variability. The 50% flux reduction observed in one MIRI filter between observations a month apart remains a puzzle that the new spectroscopy may or may not directly address. Month timescale variability in mid-infrared FLUX is unusual for either a cooling merger remnant or a steadily accreting black hole. Some researchers have suggested this variability could indicate clumpy dust structure around the source, with the apparent brightness changing as differently dense clumps of material pass in front of the emitting region as it rotates, or as the dust distribution evolves. The broader context for this program is the ongoing operation of Kochenik's failed supernova survey, which has continued to monitor red supergiants in nearby galaxies for additional disappearance candidates, while N1646BH1 remains the best studied case. Several additional candidates have been identified in the survey data and are at various stages of follow-up analysis. As JWST becomes available to study each of these candidates with the kind of detailed infrared observations applied to N6946BH1, a study's tickle sample, rather than a single case study, may begin to emerge. For the Kinman dwarfs vanished LBV, the most significant anticipated development remains the extremely large telescope, whose construction has continued through 2025 and 2026, with first light still expected before the end of the decade. The ELT's 39-meter primary mirror and advanced adaptive optics will provide angular resolution sufficient to potentially resolve individual bright stars in galaxies like the Kinman dwarf for the first time. either confirming the continued presence of a surviving star, or confirming its absence and strengthening the case for either a failed supernova or an undetected historical supernova. For Assassin-24 FW, the August 2025 dust occultation explanation remains the leading interpretation, though continued monitoring of the star's brightness and any future dimming episodes would help confirm whether the dust structure responsible for the 2024-225 event is a transient feature or part of a recurring pattern, which would have implications for whether the star is shedding material episodically, a behavior associated with certain phases of massive star evolution. The resolution of the N6946 BH1 mystery, whenever it comes, will have implications that extend well beyond a single star in a single galaxy. If N6946 BH1 is confirmed as a failed supernova, it would represent the first direct observational confirmation of a process that has been a standard part of stellar evolution theory for decades, but has never been directly observed. This would have several downstream effects. It would provide an observational anchor for the rate at which massive stars produce failed supernova versus conventional supernova, a parameter that feeds directly into models of galactic chemical evolution, black hole mass distributions, and the population of black holes available for gravitational wave merger events detected by LIGO and similar observatories. It would help resolve the red supergiant problem, the puzzling absence of very massive red supergiants among observed supernova progenitors, by confirming that at least some of these stars do not produce supernova at all, removing them from the progenit or catalog entirely rather than hiding them behind dust. And it would validate Kochenek's survey methodology, potentially leading to expanded efforts to monitor nearby galaxies for additional failed supernova candidates, with the goal of building a statistical sample large enough to constrain the failed supernova rate precisely. If N6946 BH1 is confirmed as a stellar merger, the implications are different but equally significant. It would represent the most massive, most distant, and most thoroughly observed stellar merger in history, providing a dataset for merger physics models that current observations of less massive, closer mergers, like the well-studied merger in the Milky W's V39 Scorpii, cannot match. It would inform models of how binary massive stars evolve and interact, a topic of intense interest because binary massive star evolution is directly connected to the formation channels for binary black holes, the kind that LIGO detects merging via gravitational waves. And it would suggest that some fraction of the apparent disappearing star candidates in Kochenek's survey may be mergers rather than failed supernova, requiring a re-examination of the survey's other candidates with this possibility specifically in Min-D. Either outcome advances the science, neither outcome is a failure of the investigation. The broader lesson, one that applies to N6946 BH1, to the Kinman dwarf's vanished star, and to the general project of understanding how massive stars end their lives, is that the universe's most dramatic transformations often happen too quickly, too far away, or too obscured by dust for us to observe directly. We see the before, we see the after. The in-between, the actual moment of transformation, is usually hidden. JWST is changing this, incrementally. Its infrared sensitivity penetrates dust that optical telescopes cannot see through. Its resolution distinguishes sources that blur together at lower resolution. Its spectroscopic capability provides diagnostics that B-Roadband photometry cannot. The next decade will likely see JWST applied systematically to every candidate disappearing star identified by ongoing surveys, building, for the first time, a real observational dataset on what happens when massive stars vanish. Some will turn out to be failed supernova. Some will turn out to be mergers. Some will turn out to be dust-obscured survivors, like Assassin-24 FW might have been if its dimming had been more extreme or longer lasting. And, from that dataset, a real answer to the question, how often do massive stars die quietly, will finally emerge, not from theory, but from observation. And here is what makes the story of N6946BH1 and the broader story of disappearing stars truly remarkable. For the entire history of astronomy, the death of a massive star has been one of the most observable events in the universe. Supernova are not subtle. They are visible across billions of light years. They have been recorded by human civilizations for thousands of years. The supernova of 54 that created the Crab Nebula was recorded by astronomers in China, Japan, and the Arab world, bright enough to be visible in daylight for weeks. Massive, stellar death has always been loud. And now, for the first time, we have a star, possibly several, that died quietly, that simply disappeared, no flash visible across the galaxy, no record for future astronomers to find. Just a star that was there, and then, a few years later, was not. If N6946BH1 is a failed supernova, it means that some fraction of the universe's most massive stars that have been forming and dying for the entire 13.8 billion-year history of the cosmos, have been quietly collapsing into black holes, leaving almost no trace, completely unnoticed, for the entire history of astronomy until Kachenek's survey was specifically designed to look for them. How many of these quiet deaths have happened, in our galaxy alone, that nobody ever recorded? How many black holes are sitting in the Milky Way right now? The silent remnants of stars that simply vanished, with no supernova remnant, no historical record, nothing to mark where a star used to be. If N6946BH1 is a stellar merger, the revelation is different but no less profound. It means that two massive stars, each potentially capable of producing a supernova on its own, instead spiraled together and merged, producing not an explosion visible across the universe, but a relatively modest brightening, followed by a slow transformation into something new. A single, merged, dust-enshrouded object, the product of two stellar lives combining into one. Either way, the universe did something to this star that nobody was watching closely enough to see in real time. We saw the before. JWST is now seeing the after. The in-between, the actual transformation, happened in the dark, 14 years ago, 22 million light-years away, and we are only now, slowly, with the most powerful infrared telescope ever built, piecing together what it might have been. Let that sit for a moment. The universe's most violent transformations, the ones that forge the heavy elements in our bodies, that create the black holes whose mergers we detect as gravitational waves, that determine how galaxies chemically evolve over cosmic time, are not always visible. Some of them happen quietly, some of them happen in the dark, and the only way we know they happened at all is because, years later, something that used to be there isn't. The star that vanished did not vanish without a trace. It left a question, and the answer to that question, whichever way it resolves, will tell us something true about how the universe builds and destroys its most massive objects, in the light and in the dark, observed and unobserved, for the entire history of time. But there is one more piece to this story. Because if some massive stars die quietly, collapsing to black holes without announcing themselves, then the Milky Way itself should contain examples Black holes that formed not from observed supernova, but from quiet collapses that nobody recorded. See Ting in our own galaxy, possibly close to us, completely undetected, except through their gravitational influence on nearby stars. In recent years, astronomers using precise stellar motion data have begun finding exactly this kind of object, isolated black holes, with no companion star, no accretion disk, no X-ray emission, detectable only because they bend the light of more distant stars as they pass in front of them. How many of these silent black holes are out there? And what does finding them tell us about the population of massive stars that died without anyone ever knowing? That is a story for next time. Tonight, we did not just learn about a star that disappeared. We watched what happens when the universe does something quietly, something that, by every expectation of stellar physics, should have been loud, should have been visible, should have announced itself across the cosmos, and instead simply happened, in the dark, without ceremony. We saw Christopher Kochenik build a survey specifically designed to catch stars in the act of vanishing, because theoretical physics predicted that some of them should. We saw N6946BH1 brighten modestly in 2009, then fade, year after year, until by 2015 it was gone from every optical image. We saw JWST in 2023 look at the same position and find something still there, fainter, transformed, glowing in the infrared, in a way that 14 years of theoretical work still cannot fully explain. We saw a parallel mystery in the Kinman dwarf galaxy, a massive star whose signatures vanished from spectra between 2011 and 2019, with nobody watching closely enough to know exactly when or how. And we saw, in Assassin-24 FW, what it looks like when a disappearance is explained, quickly, cleanly, through careful attention to a single diagnostic clue. The color of light that didn't change. The contrast between these stories is the lesson. Some disappearances are explained in months. Some remain open after 14 years, and the deployment of the most powerful infrared telescope ever built. The universe does not owe us easy answers, but it is, slowly, patiently, giving us the tools to find them. The central question, what is N6946BH1, actually, remains unresolved as of May 2026. JWST program 7648 has been approved and will provide the mid-infrared spectroscopy needed to test the PAH emission diagnostic that could distinguish between the stellar merger and failed supernova scenarios. The data from this program has not yet been obtained or analyzed as of this recording. The month timescale variability in the infrared source. The 50% flux drop observed between observations 1 month apart remains unexplained by any of the 3 leading scenarios in their simplest forms, and may require additional physical mechanisms SMS, such as clumpy circumstellar dust, to fully account for. The fate of the luminous blue variable in the Kinman dwarf galaxy remains unknown. Whether it survived in a dimmed and dust-obscured state, collapsed to a black hole without a supernova, or had already exploded in an undetected supernova before 2001, awaits resolution, likely from the extremely large telescope, whose first light is still pending. The broader statistical question, what fraction of massive stars die quietly, without a supernova, remains an open problem that the ongoing failed supernova survey and JWST follow-up observations are working to address, one candidate at a time. There are a few things worth taking from this story that go beyond any single disappearing star. The first is that absence is data. N6946BH1 disappearance was not a failure of observation, it was the observation. The survey that found it was specifically designed to detect absences, and the absence it found has been scientifically productive for early 2 decades, regardless of which final interpretation turns out to be correct. The second is that it disappeared and gone are not the same thing. N946BH1 disappeared from optical view in 2015. It was not gone. JWST found it again in 2024, transformed, fainter, but present. The universe's transformations are often partial, ongoing, and visible only if you look in the right wavelength. The third is that the color of light carries information that brightness alone does not. Assassin 24 FW's color, constant dimming, was the single clue that distinguished something is blocking this star from a this star is dying. The same principle, using multiple independent observables to distinguish between competing scenarios, is exactly what JWST program 7X48 is attempting for N6946BH1, using spectral shape rather than color, but the underlying logic is identical. The fourth is that some of the universe's biggest questions are answered by patient accumulation, not single dramatic discoveries. The failed supernova rate, the stellar merger rate, the true extent of the red supergiant problem, none of these will be answered by N6946BH1 alone. They will be answered by N6946BH1, plus the next candidate, plus the one after that, plus the Kinman dwarf's resolution, plus whatever the extremely large telescope eventually reveals. Science, at this frontier, is cumulative, and the fifth is this. We built a survey to find stars that quietly die. We found one. 14 years later, we still do not know exactly what happened to it. And the not knowing is not a failure. It is the most honest possible description of where the frontier of stellar astrophysics actually is. So I want to leave you with a few questions tonight. If N6946BH1 turns out to be a failed supernova, the first ever confirmed, what does that mean for every massive star we can currently see in the night sky? How many of them might end the same way? Not with the explosion the textbooks promise, but with a quiet fade into darkness. If it turns out to be a stellar merger instead, does that feel like a less dramatic answer? Should it? A merger of two massive stars, observed in unprecedented detail across 14 years and multiple space telescopes, is itself one of the rarest events ever documented. And, at the broadest scale, how many transformations is the universe undergoing right now that nobody is watching closely enough to see? How many stars have already vanished in galaxies we have not yet looked at carefully, leaving behind exactly the kind of quiet absence that took a dedicated survey and nearly 2 decades of follow-up to even notice once? Sit with that. The universe is not silent, we just aren't always listening in the right way. If this story stayed with you, tell me in the comments, which moment was the one that pulled you in? Was it Kachenek's survey, built specifically to catch stars in the act of disappearing? The 2024 JWST data showing something still glowing where N6946BH1 used to be. The Kinman dwarf's vanished luminous blue variable, gone sometime in an 8-year gap nobody was watching. Or Assassin -24 FW, the disappearance that turned out to be a shadow, not a death. I want to know. And if you want more stories like this, real astrophysics at the edge of the unknown, told honestly, subscribe to Galaxy Pulse. We go beyond the headlines every single time. I will see you in the next one. In 2009, a star 25 times the mass of the Sun brightened slightly. By 2015, it was gone. In 2024, something was still there, fainter, changed, refusing to fit any simple explanation. We do not know, yet, what happened to it. But we know this. Somewhere, 22 million light years away, the universe did something extraordinary, and it did it quietly,